Okay, now let's move on to warm up number 2. So question number 11 says how many pieces that are exactly 5 inches long can Sue cut from a string that's 7 feet long? So the easiest thing to do, I think, would be to convert these 7 feet into inches. So if I know that there's 12 inches in a foot, that's going to be 84 inches. So now, if I want to know how many pieces that are exactly 5 inches long can she cut, that's going to be 84 divided by 5. And remember, we're still doing warm-ups, so no calculators. So 5 goes into 8 one time. So that's 6. And then I've got a remainder of 4, but the question is how many pieces that are exactly 5 inches long can she cut? So the answer should be 16. And it is. Now let's go on to question number 12. Question number 12 says, how many units away from the origin is the point -3, -4? Well, let's draw our axis and remember that the origin is right here at 0, 0. And so this point is going to be, if this is my x and this is my y, so this point is going to be 1, 2, 3. There's -3, and that's going to be down 1, 2, 3, 4. There's -4. So it's going to be about right here. So the question is, how many units away? So this is really a triangle problem. So if we draw our triangle, because here is our point, here's the origin. That was not a very good line, but this makes a triangle right there, right? So this side of the triangle is 4 units long, this side of the triangle is 3 units long, and remember from warm-up number 1, our Pythagorean theorem says that a squared plus b squared equals c squared. C is always the hypotenuse, which is what we're solving for. And so we've got 3 squared plus 4 squared equals 6c squared. 9 plus 16 equals so c squared equals 25, c equals 5. And so what they were trying to get you to see is that this is a common one. They call it the 3, 4, 5 triangle, which means if these two are 3 and 4, this one has to be 5. It's just the only way that this one's going to work out. So our answer should be 5, right? Our answer is 5 units. Number 13. Number 13 says, a hexagonal table that is by itself seats 6 people, 1 person at each side. So here's our hexagon table. Let's see if I can, my hexagons are not good. It's not terrible, right? So a hexagon, 1 person at each side, 1, 2, 3, 4, 5, 6, for a total of 6 people. A row of hexagonal tables is created by pushing together a certain number of these tables so that a side of one table meets a side of the next table. If 50 people can sit at the row of tables, how many tables are in the row? So if we just start putting hexagons side by side until we can get 50 people, how many tables would we need? Well, what ends up happening is, except for the ends, we lose 2 spots for each table. So that means that we're going to have 2 tables, so the ones on the 2 ends, 2 tables that will seat 1, 2, 3, 4, 5. And then X tables, that's what we're trying to solve for, that are only going to seat 1, 2, 3, 4. But it's going to give us a total of 50. So 10 plus 4x equals 50. 4x equals 40 if I move that 10 to the other side. So x has to be equal to 10. So it should be 10 tables. Oh, not 10 tables. X is 10, but I can't forget this. So I've got 10 tables that seat 4 plus 2 tables that seat 5 for a total of 12 tables. So our answer is 12. Okay, number 14. In Oregon, which has no sales tax, Gloria bought 3 notebooks for $1.57 each. If she paid $5, what is the least number of US coins that she could get in change? So there's no tax, so we don't have to worry about that. So how much was her bill? Let's see, $1.57 times 3 is what she owed. So 7 times 3 is 21, 5 times 3 is 15, plus 2 is 17. So she owed $4.71 for the notebooks. If she paid $5, how much change was she owed? $5 minus $4.71, so what's that, 29 cents? Okay. And so the question is, what's the least number of US coins that she could get in change? Well, we want to use the largest coin first, so clearly she's going to get a quarter. And the only way I can see is that she's got to get 4 pennies. So it should be 5 coins. And that is correct. Okay, let's do one more and take a break. Number 15. Oh boy. The mass of a fluorine atom is 3.16 times 10 to the negative 23 grams. What is the mass of 1 million fluorine atoms? Express your answer in scientific notation to 3 significant figures. So what we're trying to do is multiply this guy, this thing, by 1 million. So you could say that it is 3,160,000 times 10 to the negative 23. But we have to express our answer to 3 significant figures. So since we're using 3 significant figures, the easiest way to do this then would be to recognize that in scientific notation, this 1 million is really just 10 to the 9th power. And so the way you can think about that is look at the number 10 to the 9th power. Oh, I wrote the question wrong. It's not 1 million, it's 1 billion. It's the number of zeros. So this was never going to work. So we have this many fluorine atoms, not 1 million, 1 billion. And so I've got 9 zeros, so that makes this equal to 10 to the 9th power. So now it becomes really simple because now I'm just adding exponents. So I'm taking, it's kind of like a question that we had before. I'm going to take 3.16 times 10 to the negative 23 times 10 to the 9th. And so I can just do 3.16 times 10 to the, and I'm going to add these exponents. So this is going to be 9 minus 23 or minus 14. And that would be 3 significant digits. So let me make sure we're right. We are. Okay, so let's stop here and then we'll come back and finish up this one.